di variable modo. And he will talk about Cauchy limit, that semiclassical perturbation of nonlinear Schrödinger equation. Okay, Marco, you can start.
Thank you, Sabina, for the introduction. And thanks to Caterina and to all the organizers. I hope I didn't forget anyone here, or for the invitation and for having organized this series of talks, which are in some ways, as I was saying before, impossible to be held in person. So I think that this is one of the good things that this pandemic brought to us. Okay, as Sabina was saying, I will talk about some nonlinear Schrödinger equations. So we're talking about PD and so analysis, and in particular we'll focus on some kind of perturbation given by a potential, which in physics is sometimes called semiclassical. So this is the framework, and so let's begin. And one of the equations which will be of interest, but not the one that we're going to study, is this one. And but we will use this equation. So first of all, let's present the guest. And okay, here we have the classical Laplacian. Here we have u, which is the unknown, the function unknown of our equation. And then we have a constant here, which is fixed and positive. And then we have a nonlinearity, which is quite general, but okay, I will see something better about this later. And okay, you may think about a power if you prefer. And okay, we are working in Rn in the entire space. Okay. And I think that I want to highlight from the beginning, because it will be of key importance or throughout all the talk, is that this equation is invariant by translation. What I mean that if we have a solution of this equation and we consider a translation, then a translation of the solution, we still have a solution. And this is said sometimes that the equation is autonomous. And this is given by the fact that this coefficient is constant. And this will be, as I said, of key importance, especially from a negative point of view, in some sense. Okay, and just to be clear of what I mean by solution, even if it will be of no importance, actually, in what I will say next, by solution, I mean a weak solution that is considered a fractional, so we are in a variational framework, a function defined on a sublet space, which consider integrals and the antiderivative of the nonlinearity. We say that U is a weak solution of this equation if it is a critical point of the functional. And okay, but as I said, it is not important. I will talk about functional only at the end of the talk. So if you prefer, if you are not used with this notation, you may think about solution just as a pointwise solution, as classical solution. Okay, the most intuitive definition that you can give to this equation. And okay, as you can see, I will not write the x anymore, just to give a more clear notation. Okay. So, as I said, this is not the equation that we're going to study, because essentially about this equation is known quite everything given by Bereziki-Lyon. And in particular, we know that there exists solution of this equation, and in particular, there exists ground states. Okay, in order to talk about ground states, I should talk about the function that I introduced before, saying that ground states minimize the energy, but if you are not used with this, you may think ground states only as special solution. Okay, some particular solution which enjoys more properties. So when I will say ground states, you may think about just this. And okay, we know also more, and we know also that the ground states have a shape something like this. Okay, so with a maximum and then they decay. And again, let me remark that since the problem is autonomous, if this is an equation and we translate this in a point P, then we still have a solution, we still have a ground states. So in particular, the solutions are not unique in this case. Okay, so just a few words. I don't want to bother you with the assumption on F. Let me just remark that, okay, these are the assumptions and they are almost optimal in some sense. And in particular, we are assuming the function F subcritical. But okay, it's not important what we are assuming now. And as models, as examples, you may think about pure powers or sum of powers, which usually means cooperation in models, or difference, which means competition, or also other models, which usually arises in nonlinear optics, for example. Okay, so this is these are the assumptions. And okay, now I want to present what is the problem that we're going to study, which is actually will be this one. And okay, let's consider a potential V, which is positive. And okay, if you consider a parameter epsilon, for small values of epsilon, you may see that in some ways this quantity is approximately equal to V0. And okay, and we ask V0 to be equal to the constant that we fixed at the beginning, so M0. So you can see that in some ways, this equation that I presented before is a limiting equation of this one. So by sending epsilon to 0, we have that we regain this equation. So what we're going to study is this one, in particular when epsilon is small. Okay, this is the goal of this talk. In particular, we want to search for solution of this equation, and then we will ask also what happens when epsilon goes to 0. Okay, and let me first say a few words on why this equation is important, some physical motivation. And okay, this is the equation. And as you can see, I didn't specify it before, it is not autonomous, okay? Because there is a potential with dependence on x. Okay, as I was saying, consider this equation, consider a change of variable. So the epsilon come up here. And if we write epsilon as this quantity, which is the usual one, which is present in the Schrödinger equation, so h bar is the Planck's constant and m is the mass, then you can see that asking epsilon go to 0 means that the mass, in some sense, is going to infinity. So we are going from small quantities to big quantities, from the microscopic to macroscopic. In some ways, we are going from quantum mechanics to classical mechanics. Okay, of course, this is just an idea, and this is why these equations are called semiclassical. And okay, but of course, there are more details on these, but I will not give them now. And okay, so what is the strategy? How we find a solution of this equation? Well, the idea, as I said before, is to look at this equation and say, okay, solution of this one, which I will write with small u, are in some sense perturbation of the solution of this one, which I will write with capital U, just not to make confusions. And okay, so this is the idea. In particular, I will search for a neighborhood of solution of this equation, and then I will search for a neighborhood. Okay, the first was a set, then we search for a neighborhood where to find u. Okay, this is the idea. And let me just remark that the solution of this equation are not explicit in general for general nonlinearity f. So we cannot use direct approaches. Okay, this is just a remark. Okay, so first of all, we want a good starting point a good set of the solution of this equation, and then we want to perturb this to find solution of our equation. So, okay, of course, the first attempt is to say, okay, let's consider all the solution of this equation. But every solution, the set of all the solution doesn't enjoy a lot of good properties. Okay, they are too general. That's why the first step is to restrict to ground states that are the ones that I was citing before, because okay, they have minimal energy and so they enjoy more properties. And so this is a good starting point, but not good enough. Why? Well, in order to get existence in analysis, but okay, in mathematics generally, a good ingredient is the compactness. Think, for example, to Bayes' theorem, for example. And so we would like this set to be compact. And but there's a problem, and this is the one that I was saying before. That is, if we consider a function u, and then we translate it with a point Pn, and we say, okay, this Pn goes to infinity, then this solution is escaping at infinity also. This means that we cannot have a compactness because solutions are escaping. So this is a problem, and we need to fix this. And okay, the idea is very simple. The idea is to consider the set, okay, of all the ground states that I defined before, which has a point, a maximum in 0. Okay, and in this case, okay, we have that the solution have their maximum fixed in 0, and so they cannot escape at infinity. And actually, with this condition, we can prove that this set is actually compact. Okay, there are techniques, technicalities with which we prove this, but I will not focus on this. Okay, now we have a compact set, which is a good starting point, and we are ready now to perturb this set in order to find solutions of this equation that I recall you is the goal of the talk. And okay, how we perturb this? Well, okay, let's take a function u in this compact set, then we translate this, and then we add also a phi, which is quite general now, but you may think this as a perturbation. So in some sense, this should be small, as I will say later. So this is a good perturbation. But okay, as you probably noticed, we make a lot of effort in order to say, okay, this is compact because there are no translations. But okay, now again, we are considering translation. Okay, of course, it may seem stupid, but it is necessary because the equation that we are going to study is not autonomous. So there's no hope in saying, okay, we can ignore translations, okay, because we want solution of a non-autonomous equation. Okay, but the works that we did is not completely lost because we can use now that this set is actually compact. Okay, and the goal now is how do we regain compactness of on this set? Okay, and the idea is to bound in some ways these two bad guys. Okay, as I said, okay, we want to bound this one and this one in order to regain compactness, because okay, boundedness it's a first step for compactness. And the problem is that okay, taking u in this set, we know that there exists a p, there exists a phi, but we don't know who they are, and we don't know if they are unique. Okay, so we cannot address to each u a p and a phi uniquely. And that's why we want in some ways to find approximation of this p and this phi and say, okay, we have them, and we can see that they are bounded. So focus first of all on phi, which is the easier one. Okay, you can see that phi is the difference of these two quantities. So the norm. And but okay, as I said, we don't know u, we don't know p, so it is not useful to use this expression. But we can say, okay, let's consider the infimum all over the W in this set of compact, in this compact set of ground states, and all the Q in Rn. So in this definition, you see that there is no U and no P, no particular U and P, but in some ways you may understand that this hat row is approximately equal to the norm of phi. And okay, so this is the first definition, and we say, okay, rho hat is small, and we are regaining compactness, at least for this first step. Now the problem is to find and to bound this P, which is a little trickier in some ways. And let's see how to do this. Well, as I said before, now phi is small. You have to think phi as small because we said this. And okay, all the functions in S hat have the maximum in 0. And so u minus pi minus p has the maximum in p. And so you can see, okay, then we add phi, but phi is just a small perturbation. And so you can see that in p, actually most of the mass of the function, which is given by the norm, okay, but it is not important, is centered in p. Okay, so in some ways p can be considered as a center of mass. Okay, and now we wonder, how do we find a center of mass of something? And the idea is given by physics, which says, okay, usually the center of mass of a body is given by the integral of density times the point over the integrals of the density. Okay, this is a quite standard definition of center of mass. And this is what we do in order to define the center of mass of a function u in S prime. Of course, we have to define the density, but we will see this in a moment. So by the intuitive fact that I said before, gamma u is actually approximately equal to p. And so the idea say, okay, gamma u is well defined. We say gamma u is bounded. So in some ways, also p is bounded, and we regain compactness. Okay. Now, the question is how to define the density. And of course, since P is the center of mass, the density of in a point Q should be big when Q is near P and small where Q is distant from P. But of course, this definition is not good because we are using P and we don't know P. Our goal is to find P. And okay, so we change a bit the things, and we say, okay, we have a function here with p that we don't know, and then consider another function in q, and say, okay, consider little neighborhood near q and p, and say, okay, if this is u, more or less. So if you consider the difference of u and these other ground states, which has been translated, and its difference is big, it means that q and p are far from one from the other. If instead this difference is small, it means that q is near p. And this is a better definition because, as you can see, P doesn't appear anymore. But okay, there's again a problem because we don't know U, But okay, now you understood how to fix this problem. And we fix this by taking the infimum all over the function in W. And here, even if I'm not saying this explicitly, we are using the fact that S hat is compact. And so this infimum is well defined in some ways. And okay, everything can be done in a proper way because S hat is compact. Okay. And okay, so to be more precise, the definition is given by this expression modulo cutoff function, but okay, it is not important how this cutoff function is made. Now we have a definition which is not ambiguous because u, p, and phi doesn't appear. And so this is a good definition for the density, and so a good definition for the center of mass. And okay, so we're done because we have an approximation of phi, and we ask it to be small. We have an approximation of p, and we ask it to be bounded. And so in some ways, we regain the compactness that we lost before. Okay, this is given by Paris-Smith condition, deformation lemma, and so on. Okay, I will not bother you with these things. And okay, as I said, compactness brings to existence of a solution. And so we have that for small epsilon, there exists a solution u epsilon of this equation. And moreover, by the construction of this that we made, u epsilon converges to ground states of the limiting problem. Of course, up to a translation because there is some p which makes some noise. Okay, this was a first step, a first goal. But now we want more. We want to prove more and investigate better what happens when epsilon goes to 0. And okay. And what we want to prove is a concentration phenomena. So let me explain this better. And consider again the solution by scaling that I introduced before when I talked about physics. And okay, we wanted to prove that this solution concentrate some sense somewhere. And okay, let's see this better. And first of all, let me remark, even if I didn't mention it before, that in all the things that I said, x0, which before was just 0 to make everything simple, is actually an infimum, a local minimum in a bounded set of Rn. Okay, to make everything simpler, just think x0 as a strict, unique point of minimum in this omega. Okay, so as I said, we want to prove that this function is concentrating in omega. And okay, here there is the precise definition, but you may think only to the fact that the v epsilon is getting closer to omega, that the mass of v epsilon is getting closer to omega. Okay, this is just the idea that you have to keep in mind. And okay, and since we wanted to do computation with u epsilon, by scaling, we wanted to see that u epsilon get closer to omega over epsilon. Okay, this is just a matter of how the scaling works. Okay, so this is the goal. And what is the idea? This is the point where functional comes into play again. So sorry if you are not used with functional. And okay, but just follow me with the basic idea. Let's consider this functional, okay? And it is made by an integration outside omega or epsilon, okay? Coefficient, and then -1 and a positive part. Okay, focus first on Q1, so there is no epsilon practically. And okay, if this quantity is equal to 0, then this means that this quantity is small. Why? Because small minus 1 is negative, taking the positive part, it is equal to 0. And okay, but if this is small, this means that U has much mass inside of omega, okay, because integration outside of omega is small. Okay, this is a good point. And that's why if we make the same argument with Q epsilon, you can see that U has much mass inside omega over epsilon. And in this case, I say very much mass because the smallness of this piece has to compensate this piece with going to infinity for epsilon going to 0. Okay, so that's why Q, this relation risks the fact that U epsilon is getting closer to this set. Okay, so let's see how to use this idea. And I said before, let's consider again the functional. And I recall you that the solution of this equation are points which make the gradient of the function equal to 0, critical points. And okay, the idea is to consider a modification of this functional, adding the one which brings concentration from the beginning. And if we make all the computation with this functional, what happens? Well, okay, we find critical points, and moreover, one can prove that through the use of quantum function, okay, I have no time to give details, but one can prove that actually this quantity is equal to 0. What does it mean? First of all, it means that we have concentration. We introduce it for this purpose. And moreover, we have, okay, this is 0, so it is not present. So critical points of this functional are critical points of this functional, and thus solution of this equation. And okay, so we are practically done because okay, here there is the theorem that I talked about badly, but okay, I have no time to give details. Theorem given due to Cingolani and Tanaka, which says, okay, in the assumption that I said before, plus something else, we have the existence of a solution, and we have the convergence to our ground states, and the concentration in omega. And okay, this is actually the result. And now I would like to spend a few words on what I did in my research. And it is the generalization of this result to a fractional framework. So first of all, let me introduce the fractional relation, which is this bad guy. And even if it doesn't seem very similar to the classical Laplacian, it is important to know that when S is going to 1, this quantity converges to, in some sense, to the classical Laplacian. Okay, so I said 1 because this power is given by S between 0 and 1, and that's why it is called fractional. And okay, the most important thing of this operator, the most bad thing, is that this operator is non-local. What I mean by non-local, I mean that in order to compute the operator in the point x, it's not sufficient to know the values of x or of the function in a neighborhood of x, like for the computation of the classical derivative. But we need to know the values of the function all over Rn. That's why it is called non-local. Of course, this non-locality brings to many difficulties. One of them is the use of cutoff function, because the support of the function of the operator is not, the support of the subfunction is not conserved by the operator. Of course, it is because of the non-locality. And another problem is the localization of the center of mass, because we said, okay, we want to know where the center of mass is. And of course, with a non-locality, it's difficult to localize something. But okay, and it translates in the right choice of norm in the definition of the center of mass, a norm which controls also details of this operator. Okay, there are also other technical difficulties, but I will not focus on this. And okay, so actually, in collaboration with Professor Cingolani, we proved this result for the fractional Laplacian, gaining again the existence of the solution, the convergence of ground states, and the concentration in omega. And okay, we are almost done. I just want to remark that actually the results by Cingolani and Tanaka, by me and Cingolani, actually deals with not only the existence, but the multiplicity of the solutions. And it is done by considering the set of the local minima, so not only a single minimum, and considering the topology of K, and the topology of K brings the more solution to the problems. Okay, but I don't want to focus this. Okay, I think we are done, and thank you to everybody for your attention.
Okay, thank you, Marco, for the